Okay. All right. So last time we were talking about insertion sort, we said that the worst case analysis gave us what complexity? Theta n squared. And that occurs when what? What does the data look like for the insertion sort in the worst case? Reverse order. Reverse order. Yep. So reverse, not just a little bit off, completely reverse. That happens to be the worst case. Okay. Now the average case, we're going to say all permutations, and you know there's a lot of permutations, all permutations are equally likely. So we're going to have for all of the algorithm from 2 to n, we're going to say basically that we're going to have, roughly speaking, half this, what's the word we're looking for? Sliding, right? Half the elements are going to slide. So when j goes to n, it's going to be n over 2. When j goes to 4, it's going to be 4 over 2 or 2. So it's always going to be about half. Because remember, whenever you take an element out, it's always going to be from 2 to n. So if we take out this one, and this one is, for example, n over 2, there are only n over 2 elements in front of it, so that's the worst it's going to be. Right? Okay. So we still have a theta of n squared. So we're going to look at a different algorithm, which is going to give us a little bit of a different complexity. And this algorithm is called merge sort. How many of you have heard of merge sort? So merge sort is an interesting algorithm. It can be implemented either recursively, but it can also be implemented easily iteratively without recursion. This is the pseudocode, or the high-level code for merge sort. The idea is you want to merge sort an element array from 1 to n. Okay? And so if n is equal to 1, then you're done. Why? Because sorting a one-element array, you're finished. Because one-element array is always in order with itself. The smallest element is the largest element, is the only element sorted. Okay, but if your size that you're sorting is not equal to 1, then what we're going to do is we're going to go from 1 to n over 2 ceiling, which is going to give us someplace in the middle. For example, if we had n was 16, then this would be 16 over 2, 1 to 8. And this would be 9 to 16. It would just split it right in half, right? And then what we will do is we'll recursively merge sort this one. So just imagine that we have 16 is n. So 16 is going to go to what? It's going to recursively merge sort 1 to 8. Which is going to recursively merge sort 1 to 4, which is recursively going to sort 1 to 2, which is recursively going to sort 1, which is done, then the other one, which is done, and then it's going to do what? It's going to then merge them. So those two elements are going to get merged. So that's the way merge sort works. So basically it keeps going until it gets to the singles, then it merges them, and as it goes up, those doubles become merged, so then it merges those into fours. The fours becomes merged, so they become eights, etc., until we get to the full size. All right, so the key subroutine is merge. So this is the algorithm, and this is the recursion once on the left side, and a recursion once on the right side. So suppose that we have these two lists here, right? So we have these two elements. So right now, are these in order or not in order? So we have 2, 7, 13, 20. That's in order, right? And then we have 1, 9, 11, 12. So for example, if we were doing an n equal to 8, and I would recursively sort left part, which is 4, and recursively sort right part, which is the other 4, eventually it will go deeper recursively and come back. When I come back, the first 4 is sorted, and the last 4 is sorted, and it might look like this. So now it's up to me to merge the two sorted lists. So that's easy, right? So in this case, we're going to compare 2 and 1. Which is the smaller one? So we're going to take 1. And then our pointer goes up to 9, because we used 1. So now we compare 2 against 9. And which one is the smaller? Again, at this point it's going to be 2. So 2 will go out. And that pointer goes up to what? Goes to 7. Right? Goes to 7. So now we have 7 and 9. 7 goes down. We have 9 and 13. 9 goes down. We have 11 and 13. 11 goes down. We have 12 and 13. 12 goes down. And at that point, this list is empty. So what do? We just take everybody from the other list in order. Okay, so that's the merging. What is the complexity of the merge that we just did? Well, the complexity of the merge, basically, what we're doing is, let's count the characteristic operations. How many characteristic operations do we have? And what is the characteristic operation? The comparison. The comparison. So right now we're doing a comparison, right? So that's a comparison. 2, 3, 4, 5, 6. Now, technically speaking, if it just happened that these last two are the biggest, right? But for example, if this was an 18, we'd have a 6th comparison and a 7th comparison before we could put the final element in. So in case of 8 elements, what's the most comparisons you're going to have? N minus 1. Or in this case of 8, it would be 7. So if you have, let's say, 1,024 elements, your worst number of comparisons, highest number of comparisons would be about 1,023. What's the least? If you have 1,024 elements, what's the smallest number of comparisons in a merge sort? And what does that mean?
N by 2.
No, not sorted. What does it mean?
Just one element.
It means that one list is completely smaller than anything in the other list. So basically what I do is I compare, this is let's say this is the smaller list, this is the bigger list. There, I'm going to merge them. So this smallest number is 1 and the biggest number is 512. But the smallest number here is 513. So every time I compare from here, I take it. Compare against the first one, take it, take it, take it, take it. I'll do it 512 times. Well, if I do it 512 times, there are no more comparisons here. This list has already been merged, so no comparisons necessary. So the least comparisons is n over 2, and so n over 2, and the greatest number of comparisons, n minus 1. Which are still theta what?
N squared.
Theta n. So the merging is a linear cost algorithm, the merging. Not merge sort, because merge sort is not just merging, it's also recursing. So we're going to be merging at every level. Okay, so time is linear, theta n, to merge a total of n elements. Just think of it as that you're comparing basically, for each element you're making a comparison. And really that may be the worst case. The only element you will never have to compare is the last element in the arrays. Because the last element will never be compared because everybody else is gone, there's nothing to compare it to. Okay, so we can do an analysis of merge sort. So here we have, if n is equal to 1, we can say that's theta 1, and theta 1 means what? That's basically constant time. What's constant time?
No. Maybe one operation?
One operation or some constant times 1. So it could be always one operation, always 3 operations. So constant time means we write theta 1, but we understand that maybe it's 2 or 3 or 4, but it doesn't depend on what? It doesn't depend on n. It doesn't depend on the size of the problem. So that's what we mean by constant time. So theta 1 just means constant time. That means one or a few operations, not a function of the size of the problem. Now we recursively sort from 1 to the middle and from the right side of the middle to the end. Now those are approximately halves. And even though he said, well, it should be n here plus t of n floor here, it turns out it really doesn't matter, and our analysis oftentimes can just assume that we're going to use powers of 2 or 2 to the k minus 1, which is 1 off from a power of 2. That gives us nice results. It doesn't change the complexity of the analysis at all. So recursively, we'll sort this one and this one, which are about the same. So since this is about half and this is about half, we're going to go recursively do a t of half twice. That's what 2 implies here. That means we're going to do it twice. So that's the setup. If n is equal to 1, we can say it's basically just a constant time. Otherwise, it's going to be 2 times n over 2 plus theta n. Where's this theta n coming from? That's the merge. So we always have to have two pieces in a recursive analysis. The first piece is, I call, this is the recursion, right? Tn over 2. And 2 times Tn over 2 is just more recursion. So you never pay for the recursion at the level of recursion. You pay for the recursion when you get lower. So we call this the recursive cost of the algorithm, and we call this the actual cost. So for example, if we are starting with 16 elements, in the algorithm we're going to basically do what? We're going to merge sort the left half, merge sort the right half, which is going to trigger some deep recursions. And eventually we come back. When we come back, we have 8 elements sorted and 8 elements sorted. So now we're going to do what? Merge. That's our actual cost. So that's called level 0. Level 0 is the one that you call the first time from the outside. Once level 0 is called from the outside with 8 elements, then it's going to call level 1 with 4 from the left and the other 4 from the right side, and that's now level 1 recursion. You'll see what I'm talking about. We'll have a nice diagram. We're going to look at an analysis technique called the recurrence tree, which is very, very powerful, very, very useful for solving recurrences, and it's almost like a visual, almost gives you a common sense feel to what's going on. But you got to understand the difference between the recursive work and the actual work. The actual work, how many actual operations that are characteristic are you executing at your level? So actual work level 0 is what is the merging cost at level 0? Actual work at level 1, because level 0 will trigger 2 level 1s. The actual cost of level 1 is the cost of all level 1s. In the case, it would be 2. And since there are 2 level 1s, there are going to be 4 level 2s. And so the cost of the merging on level 2s are going to be the summation of all of those. And as we're going down deeper, the number of levels is increasing exponentially, but the size of the problem is decreasing exponentially. So in a sense, we're keeping it balanced. We're having more things, we're having twice as many things, but they're half the size. Well, it sounds like we're basically staying even, right? Okay. So we're going to try to solve this algorithm complexity with a recursion tree. So this is so let's understand, so this is our T of n recurrence. This is this is the recursive cost. We twice recurse, we have the problem. And Cn means what? Cn really means what? What's another name of saying Cn? Theta n. Because Cn means some constant number n, and that's what theta n means. So proportional. Proportional means a constant times. Okay, so Cn, where C is some type of positive constant. Okay, so now what we're going to do is, so essentially the problem drops into here, and we have it at the top of the recursion tree. So T of n is called from the outside. That generates level 0. Okay, now what are we doing at this stage? We are recursing left, recursing right, and merging. So what we're going to do is we're going to show the merging cost as a replacement for this one at level 0, and then we're going to show 2 branches going to level 1. And so what happens here, you get Cn, that's your cost at level 0, and this is what you do, this is what you recurse with this. Does that make sense? So now we are seeing level 0 here, we have seen 2 level 1s. But now, from the level 1 perspective, when n comes in, n over 2 comes in, then we're going to left n over 4, right n over 4, and then we're going to merge. So our cost is going to be what of our merging at this level 1? Well, our input size was n, and our cost was Cn. Our input size is n over 2, so our merging cost is going to be Cn over 2. Here, and then again here. And so that's what we're going to have. So we have C of n over 2, and C of n over 2. And of course, each level 1, recursive level 0, recursive level 1, recursive level 2. There are now 4 level 2s. Each of them is taking a quarter of the problem, and you can see what's going to happen here. This is going to be the same thing, right? Cn over 4, Cn over 4, 4 times, and then we're going to generate 8 level 3s, right? Make sense? So, this is going to continue Now, how long can it continue? How high can this tree grow? Well, this tree cannot grow any higher than log base 2 of n. Because log base 2 of n is the function that tells us how many times n can be divided in half. So if you start with 16, one division makes 8, 4, 2, 1. So when you take 16, 4 divisions give you unity. That means a problem of size 1. If you have 32 to start with, if you divide it, you get 16, 8, 4, 2, 1. Now you're 5. So the height of this recurrence tree cannot be any higher than approximately, proportionally, log base 2 of n. Does that make sense? Now, what we want to do is, so you understand what is the total cost of work on level 0. What is the total cost of work at level 0? What is the total cost of work at level 0? Guys? This is not a hard question. Cn, right? What is the total work cost at level 1? That's going to be Cn over 2 plus Cn over 2, which is going to be Cn. So would you say the work at level 1, which is only one occurrence of level 0, and the two level 1s are the same? And that's what we're talking about. That the problem size is going into a half, but they're twice as many, such and such. Okay. So, and what do you think is the amount of work totally done at level 2?
Cn.
Okay. So you can see that there's a constant. Okay. There. So therefore, what we're going to do is we're going to go and we're going to tally up and sum up the total number of work. So Cn plus itself is just Cn. Cn over 2 plus Cn over 2, Cn. Cn. In fact, you can see that this is always going to be Cn. And so, how many nodes are at this level 0? 1. And how many nodes do you expect to have at this bottom level? So you expect to have not n levels, but how many nodes do you expect to have at this level? N. Each one of them doing how much work? Unity. Okay, so the size or the height here is going to be LGN. LGN, right? And now what we're going to do our summing on the right-hand side, so we can see there's Cn here on level 0. There's a total of Cn, level 1, and a total of Cn at every level. It's constant, okay? So what we want to do is we want to find out how much work is being done. Well, we know the number of leaves are going to be n, because each of them is going to do unity work. So n times 1 is going to be n. That's our theta n. This is, again, the C is just to make you feel good. We don't have to have the C. C could be 1. If C is 1, which is possible, then everything is just n, and theta n is still good. So the thing is, we have n plus n plus n plus n plus n. We have how many times n? And the answer is the number of times we have n is LGN. So we have LGN, that's how many n's we have. So we have n LGN, that is our complexity from the recursion tree. Okay? So you can say the total is theta of n LGN. The C disappears because it's just a constant. Okay, any questions about that? Hard or easy? No response, sorry.
Excuse me, Professor.
Yes, sir.
Could you please explain the log n part once more?
Yep. So basically, what we're doing is notice that because the algorithm is T of n is equal to T of n over 2, the next, from a given recursive level, the next recursive level gets half the problem size. So we keep cutting it in half. So therefore, as you take a number and you cut it in half and half and half and half and half, how many times can you do it? And the answer is log base 2 of that number. So just come up with a number like, for example, again, we're using powers of 2 because they work nicely. If you take a number like 1024 and you cut it in half, you get 512. 256, 128, 64, 32, 16, 4, 2, 1. So you're going to be able to cut that in until unity 10 times, and that's log base 2 of that number. Now, if the number is not a power of 2, then don't worry about it. Let's say the number is 1,020. Let's say 1,050. Well, you're going to still be between 1,024 and 2,048, which will be a difference of 1, 10, or 11. So your tree might not be beautifully full, but it's okay.
But the height will always be
Height
log base 2n.
Approximately be the same.
Height will always be theta log n.
N.
And specifically log. Now, why is it log 2n? Okay. When would h be equal to log base 3n?
If it is divided into 3
Divided
parts.
in 3 parts.
And
3tn.
that would, so the recurrence would have to be 3 times t of n over 3. If it was 3 times n over t of n over 2, then we have to think about it some more. Okay, so thinking is not optional. Okay, thinking is requirement. Okay, I will always try to make you think, just to move you a little bit, so that you don't just do something without thinking. I want you to think about it. Okay, so the conclusions are theta n log n grows more slowly than theta of n squared. How do we know that? How can we prove it? If I say, okay, on a homework I say, prove that theta n log n grows more slowly than theta n squared. Prove
Take
it.
some n
So log n
values.
is decreasing.
We can prove with the taking some n values.
No.
Like
That's called anecdotal evidence. Because we never can tell that if you keep, maybe if you plug in a number sufficiently high, it's going to go wrong. So,
Log n keeps
hold on, yeah, sorry. Yeah.
Find the limit of the high.
Okay, so we want to take the limit of this one over this one as n goes to infinity. And in this case, what's going to be true? This is going to be going to infinity, right? So is this. So what do we do in this case?
See which one goes faster.
So we need to find out which one is going more quickly to infinity, and we do it by what technique? L'Hopital. We talked about L'Hopital's last week, right? So we use L'Hopital's rule. So we will take the derivative of n log n. What is that? The derivative of n log n is n times lgn prime plus lgn times n prime. So what's lgn prime? What's the derivative of lgn? It's going to be 1 over n ln 2. You just multiply it by the natural log of 2. So it's proportional. So if you wanted to, you could cheat and say it's just going to be, you can just say that n lgn is really the same thing as n ln n. Why? It's not the same, but it's proportional. Because all logs are proportional. So therefore, you could say, I would like to demonstrate this is slower growing than this one by taking the limit of this over this, but I will substitute for this a proportional expression, which is n ln n. And then the derivative of n ln n is n times the derivative of ln n, which is 1 over n, which is going to be what? That's going to be 1. Plus lgn. lgn, right? And then the derivative of this on the bottom is going to be 2n. So you're going to get 1 plus lgn, still going to infinity, and 2n still going to infinity. So we can apply L'Hopital's rule one more time. So now when we apply L'Hopital's rule, we'll take the derivative of ln n, or 1 plus ln n, which is 1 over n, divided by
2.
the derivative of 2n, which is going to be 2. And that's going to go to, where's that going to go? It's going to go to 0. Because you're going to have 1 over n divided by 2. So it's going to be 1 over 2n. That will go to 0. So that's what you have to be able to do. So that proves it. As n gets large, the limit goes to 0, which means this function is growing more quickly. This one on top, growing more slowly. If I flip-flop them, if I did the limit of this over that, then that would go to what? Is there anything way I can make the limit go to constant? No. No, because these two functions are not growing proportionally. So if you put 1 on top, infinity. If you flip it, 0. They're just not proportional functions. Okay. Now, interesting point here, and I want you to remember this. Complexity is very important because it gives us the value for our function complexity for large values of n. And that's very important. But sometimes we have to be concerned about performance. And what's performance again? You know, looking at the, anybody have a smartwatch or a stupid watch? I don't know, whatever you have. We have to be concerned about performance. Performance means how fast is something working. It turns out that in practice, even though merge sort, this is the complexity of merge sort, this is the complexity of insertion sort, it turns out in practice, merge sort is better than insertion sort when n is bigger than 30. That means when n is smaller than 30, we actually get a better performance from this algorithm, which is the insertion sort. So the question is why? Anybody have an idea? But once we get over that hump of 30, then this one is just always going to be better. Any idea why?
Exponential grows slowly and
So if you were to look at the TNs of these functions, you would see that there are more instructions executing and there are more recursions, and recursions have a cost because it's calling a function. It's calling a function. So you can think of that almost as another operation, because you have to call a function, you have to return from the function, you have to call it again, you have to return, you have to do the merging, you have to allocate an array for merging. Merging is not so easy to do from an implementational standpoint. If I have an array of 1,000 elements, and I'm coming back, and I have 512 sorted from here to here, and 512 sorted from here to here, now I have to look at these elements and put them, right? Like someplace, this is going to go here, it's going to go here. I need another array, so I need more space, which means I need to allocate this array. So it takes time. So what happens is when you have a small number of elements, this overhead costs us operations and time, and merge sort underperforms for low values. And now that's a very interesting observation. But what's significant and important about that is that if you want to implement a fastest algorithm possible for large numbers, which one would you use? Would you use merge sort or this one? Merge sort or insertion sort for very large. Let's say you're always sorting millions of numbers, tens of millions of numbers. Which one would you use? Merge or insertion?
Insertion.
Okay. Some of you, all of you are wrong. Some of you are just more wrong than the others. Okay. So the people who said insertion sort are just wrong, because for very large values, it's obviously not going to be good. Now the people who said merge sort, you're not horribly wrong, but you're still not perfectly right. And the reason for that is because as an algorithm designer, you would say, well, what I'm going to do is I am going to modify my algorithm so that when my value coming in here is 30 or less, I'm no longer going to keep recursing with 32, 16, 8, 4, 2, 1. I'm simply going to call a different routine. I'm going to call insertion sort here. As soon as I get down to about 30, I'm calling a different routine. Get it? So that's the perfect answer. So yeah, so you're going to use merge sort, but you're going to complement it when you break it down small enough. You're going to finish with this, and that's very, very, very common. That's done in practical applications of these sorting algorithms that use merge sort, and another one that uses quick sort. They switch off from the recursion into an iterative insertion sort for when the problem gets small enough. So it's interesting. All right. Any other questions or comments on that?
Professor, you said that the merge sort underperforms when the number is smaller because there's a lot of allocation involved.
A lot of allocation, extra operations, the merges, the comparisons. So it's basically doing a lot of work.
Yeah. So, Professor, if the the set is actually too big, like a million or so, won't it take a lot of time to allocate like an array of a million elements or something like that?
Well, I think if you're going to implement an algorithm, you probably will immediately allocate the array and somehow use I'm going to use a static array that can be used, so that you're not always allocating it. So that when you get into practical applications, you kind of want to start thinking ahead. You try to be very, very specific versus just kind of hoping that the language is going to choose the best implementation for you. It's not going to do that. But if you use many languages like C# or Java or even C++ have built-in sorting algorithms. Well, guess what? What algorithms are they using? I'll tell you what they're not using. They're probably not using merge sort, even though it's a great algorithm. Most likely, they're using a combination of quicksort with insertion sort. That's the typical implementation for sort. And we'll talk about, quicksort is a very interesting algorithm itself and requires a lot of good thinking about it. Now, this particular algorithm, the good thing about, so let me come back to this for a second. The good thing, I'm going to go backward. Look at this, it's kind of fun. Look at that. The good thing about this algorithm is that if you think about it, if I had to, let's think about how this algorithm will behave. Let's say the data is very random, so we have very random data, and let's say what would happen to this algorithm if the data was already sorted? Well, if the data was already sorted, what I would do is I get my, let's say, 16 numbers coming in, then I recurse with 8, and then the other 8. Then from these 8, I go 4 and 4, then I go 2 and 2, 1 and 1, sorted and sorted, and then when I merge them, I'd have nothing to do. Well, I wouldn't have nothing to do. I would just basically take the first one and the second one fall in line. Then from the second 2, I would get 3 and 4, so now I would have 1, 2, and 3 and 4. And so what would happen, I would go 1, 2, 3, 4. So I compare 1 against 3, take it. 2 against 3, take it. Nothing to compare, take 3, 4. By the time I got 1, 2, 3, 4 against 5, 6, 7, 8, I would compare 1, 2, 3, and 4 against 5, and it will always be smaller. Take the first 4, no comparisons at the end. So would you call it the best case or the worst case? That's the best case because the number of comparisons in a merge sort is the minimum, which is n over 2. Okay, but is it that different from the worst case? Not really, because it's n over 2, so C is equal to 1/2. But the worst case is n, where C is equal to 1. See what I mean? So they're both linear. So it's not a big difference. So if you look over here, notice that what happens here, basically our C value essentially disappears from our analysis. Right here. C is gone. I mean, for the theta, I mean, you could add it in. You can see as C times this, but it's 1/2 to 1. Very, very small. So what I'm trying to tell you is that the difference between the best case and the worst case is almost the same. Is that a good property or a bad property to have? It's a good property when that complexity is n log n, because n log n is a decent complexity. N log n algorithms are very, very significant in engineering applications because we think of n log n algorithms as feasible algorithms for large problems. So n log n algorithms are feasible for large problems. N squared algorithms are not feasible for large problems. Think about it. Let's say your n was 1,000,000. Well, if this is 1,000,000, then theta n squared is theta of 1,000,000,000. Right? 1,000,000,000,000. When n is 1,000,000, this is only 20 million. You get the difference? So when n is 1,000,000, you're talking about 1,000,000,000,000 operations. Order of that. Here you're talking about 20 million operations. It's not even close. 20 million you can do in a fraction of a second. 1,000,000,000, not so good. Not so good, right? So you can see why n log n is so much better than n squared. It's feasible. So if we can take an algorithm and go from quadratic complexity and we can come up with an algorithm that's n log n, we have done something significant. Okay, so here we're going to take a look at something we're going to skip through because we've done them a couple different ways. I'm not going to keep repeating this stuff, but basically, everybody's going to be familiar with the big O, big omega, big theta, and also little o and little omega. Those are very important. Okay? We're not going to be doing substitution method, but we are going to get into and understand the recursion tree a little bit deeper, the power of that particular analysis, and then we're going to look at a method called the master method or the master algorithm, which is another good way of finding recurrences. So we're going to skip all this stuff here. Not interested, not interested. Little o. All right. So you can look through this. We're going to skip this one, and then we're going to go into wow, we're moving fast today. So fast it's not even turning. Okay, here we go. Okay, so the recursion tree we've already looked at, an example. So you understand what it works. Recursion tree is basically looking at the algorithm level by level. Okay? And each level, you account for its actual work in the bubble of that recursive level, and then you recurse twice, 3 times, 4 times, whatever you have, with whatever you have left over. The recursion method does promote intuition, and that's a good thing. It gives us an idea what's going on. We can see patterns for algorithms that would be relatively complicated to solve analytically. It's good for generating guesses, and sometimes it can give us results. So let's take a look at this algorithm right here. So what we have here is we have T of n is a recursive algorithm is equal to T of n over 4 plus T of n over 2 plus n squared. Now, if I asked you to write an algorithm that has this complexity, what would that algorithm look like? How does that algorithm look like if you implement it in like Java code, say? What am I going to see in that algorithm? How am I getting n squared? Say again? How am I getting n squared? Okay, so it's a nested for loop. So we're going to go 1 to n, 1 to n. That's, and we call this the what kind of work? Actual work. That's the actual work. Okay, and now how do we get T of n over 4? It's a, well, you're writing the code, right? So you have a function, bless you, you have a function called f. So how do you get this? How do you get in a function called f this? Recursive cost. You recurse? You recurse with n divided by 4. And how do you get this cost? Then you recurse. So there are 2 recursive calls. Notice it's not 2 times n over 2, because one is n over 2, the other one isn't n over 2. Okay? Everybody understand? So we have, so this is our recursive cost. These 2 are the recursive costs, and this is the actual cost. So here comes the recursion tree. So here's our input. N comes in. What's the actual cost going to be for this one? Level 0. N squared. And it will generate how many branches? 2. Why 2? Because there's 1, there's 2. Could there be 3? Sure. Not this time. Okay, so that's the 2 branches, and this time we get n over 2. And what's going to happen here in the actual work? Well, again, what happens is the n comes in, and the actual work is squaring the size. So this is going to be n over 4 squared, which is going to be n squared over 16. And this is going to be n squared over 4. So the work being done at level 1 is different here and here. Which one has more work, left or right?
Right.
More work.
Right.
It's controversial. When you square this, you're going to get n squared over 16. This is n squared over 4. Which is the bigger number?
Right.
Okay, controversy solved. Okay, everybody's happy. Okay, so a little more work. Now, So this one is doing a little more work, right? But notice that the problem size was cut in what part? In half. But this one was cut in a quarter. So now, recursively speaking, this one is going to take and split also this n over 2 in a quarter of it, and then a half of it. So what's happening is, as we're going down the rightmost branch of our recursion tree, the problem is getting cut in half, in half, in half, in half. So we know we will get to unity at log 2 of n. But if we go on the right-hand side, n over 4 is going to split it also into a quarter of that. That's going to be n over 16 and n over 8. So we're cutting this in a quarter and a quarter. Now, when we cut something into 4 pieces, think about it. Let's go with 16. 16, if I cut it into 4 pieces, what do I have? 4. If I cut it into 4 pieces, what do I have? I'm at unity. Look how fast. Wow! That was fast. How do I know how many times I'm going to, what will be the height of this unity? Log base 4n, because that's how many times you can cut something in 4. So this tree is not going to be a full tree. This tree is going to look more like this, right? It's going to look like it. And so it's going to be longer here, shorter here, and then kind of ragged looking. So it's going to be quite difficult for us to exactly get everything added up. But it's not going to stop from trying. Okay, we'll still get some very good information. Okay, so now as we go to the next level, you can see that it's going to be n over 4 squared and n over 2 squared. That's going to be n over 16. N squared over 16, n squared over 4. Well, n squared over 16 and n squared over 4, n squared over 4 is how many sixteenths? N squared over 4 is equal to 4n squared over 16. So 4n squared over 16 plus n squared over 16 is 5/16 n squared. That's the amount of work we're going to be doing at level 1. Isn't this fun? Okay, so now we're going to get n over 16. We're going to square that for the actual work. Square that, square. Notice we get 2 of these. So we're going to get n squared over 256. We're going to get 2n squared over 64 and 1n squared over 16. When you add up all these numbers, and you will add up all these numbers, and you simplify it, you're going to see that these numbers are forming a little bit of a pattern. So now, eventually, we're going to go to unity in a height of log base 4 of n here. The height will be a little bit bigger here, but not much more. I mean, if you think about it, right? It'll be shorter, but even this height is not very tall. Because even if n is 1,000,000, this is only going to go to 20. It's not so bad. Even if it's 1 billion, it's only going to be 30. If it's 1 trillion, it's going to go to 40, because it's log base 2. So that's not going to be so bad, but this one will be shorter, and it'll be kind of jagged going down to there. So now we're going to try to add up what we have. So clearly we have n squared. That's easy enough. And here I showed you that we're going to get 5/16 n squared. As we do this one, we're going to end up, if you add up all these, this is going to be 1/256. This is going to be 64ths. That's 4/256s. So 4 plus 4 is going to be 8. Plus 1 is going to be 9, so you got 9, and this is going to be 16ths, so you got to multiply it by how many? 32, 64, got to multiply it by 8. So what do we got? Well, what we got is we have 25 over 256. But 25 over 256 looks like we're squaring the 5 and we're squaring the 16. So this looks like it's going to go 5/16 n squared, and this looks like it's going to be 5/16 squared n squared. Okay? So what we have here is we are seeing a pattern that this is going to be 5/16. This is really going to be 5/16. So this is 5/16 to the 0 power, 5/16 to the 1, 5/16 to the 2, 5/16 to the 3. Now, because the tree is not full, we are not going to get a complete like this, because there's going to be some parts that are going to be dropping out from this side as this one's continuing. So that means that if we continue this, we are really going to be looking at an upper bound. Because we're not accounting for everything, we're not accounting for the drop-off. But what we're seeing is that what we have here is that we have n squared plus n squared plus n squared. If we factor out the n squared, it's going to be n squared times 5/16 to the 0 plus 5/16 to the 1 plus 5/16 to the 2 plus 5/16 to the 3, etc. How many times? I don't know exactly, but I don't care. And the reason I don't care is because I'm starting to see something very exciting, and that is, this is actually a geometric sequence with a ratio of 5/16. So therefore, if I have 1 plus 5/16 plus 5/16 squared plus 5/16 cubed, that is going to be, and the value of this ratio is going to be 1 minus 5/16 to the 5/16 to a big number over 1 minus 5/16. Well, 5/16 is less than 1. When you take the 5/16 to a big number, it's going to go to 0. So what you're going to get 1 minus 0 over 1 minus 5/16, which is 4/16. Dividing by 4/16 is like multiplying by 4. What you're going to end up having is this will all converge to 4, even if it goes on for infinity. So this whole bracket, parenthesis, is going to converge to a constant. So that means the number of n squares we have is a constant. So that means we are proportional to n squared. Does that make sense? Do we have the exact answer? No. Now, he's saying theta in a slide. I'd have to think about it. I mean, he is an MIT professor, so I got to listen to him. But I would say, I would be more comfortable saying big O. I know it's theta. But what I'm saying is we can't just jump to it like that. Because we might actually be lower than n squared. But I don't think so. You understand why? And the reason it can't be, the reason it is theta, is because if you look at this one, is there any way n squared can ever be less than n squared? No. And we know it's no more than a constant times n squared. So therefore, that's why we can say theta, because we can see that we are actually doing work proportional to n squared, which never totals any higher than a constant times n squared. Therefore, it's theta of n squared. So the geometric series gives us a huge result right here. Okay, any questions on that? The recursion tree can definitely be applied in many cases where we have 2 branches, 3 branches, 4 branches. Your job will be to basically make sure you see what's coming down, look at the actual complexity, substitute, 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 add it very carefully, see the pattern. See if you can see the pattern. Okay, if you see over here, notice that n squared is staying constant, but the number of amount of actual work, is it increasing or is it decreasing? It's decreasing. How is it decreasing? It is decreasing exponentially. It's decreasing exponentially. So it's not staying the same. That's different than merge sort. In the merge sort, we had the amount of work was staying the same across all the levels. But now we see when we add up all the levels, we actually are decreasing the work. Because 5 over 16 that's like 1/3. But 25 over 256, wow, that's like 1/10. So the work is going down, and the ratio of the exponential decay is 5/16. Okay, any questions about that? All right, interesting? I think it's interesting. All right, so now we're going to go to a very important technique that we're going to call the master method. And the master method is a technique of finding out the complexity of algorithms that fit into a certain type of recursive pattern. So in order for the master method to apply, certain things have to be true, and if they're not true, then it doesn't apply. Okay? However, I will teach you some techniques that are not in the book that allow you to use the master method as for finding upper bounds and lower bounds. As long as you understand, the master method technically strives to get the theta complexity, but in some cases where it doesn't apply, we cannot get the theta complexity. And the book doesn't go into it, but I will go into how you can still use the master method for upper bounds, which are still useful, so we can get some big O's, even if we can't get thetas. Which is more important, O or theta if we can get it?
Theta.
Theta is more important. But if we can't get it, an O, and we like the O, we'll take the O. Okay. Okay, for example, let's say I knew that my algorithm had a big O of n log n. But I thought it actually might have a lower complexity than n log n, but I wasn't able to show it. It's still good for me to say n log n. Why? Because n log n is feasible. That means this algorithm is feasible. Because if it's n log n, it's feasible, but if it's lower complexity than n log n, it's definitely feasible. So that's a good thing, right? So even though I can't say it's theta, if I can say big O of n log n, that tells me that it might be better than that, but it's already good for what I'm trying to do. So it's feasible, but I can't show that it's less than that, but I feel it is. Okay, so the master method applies to, the recurrence has to have the following format. You have to have T of n is equal to a constant A times T of n over B, where A and B are some type of positive constants, plus F of n. So let's break this down. So basically what we're saying is that the recurrence must be dividing n by some positive constant greater than 1. So typically B would be 2, 3, 4. So it's cutting that size of the problem size, right? By a factor of B, where B is at least 2, 3, 4. Typically we're talking about integers. Now, A means that not only are we cutting it into by B, but we're also doing it A times. So what does A represent?
Recursions. Number of recursions.
Yes, and what does A represent from the standpoint of a recurrence tree?
Number of branches.
The number of branches is equal to A. And the problem size cut is B. So you can have as many branches as you want in the master method, as many branches as you want, but each of the branches must be getting the same problem reduction. So the algorithm we just saw before, the 5/16, that wouldn't apply because we have T of n over 4, T of n over 2, right? So it doesn't directly apply, although I'll show you how you could. Now, so essentially all of this is the number of branches and the problem reduction, and all of that is the recursive cost. And so F of n must be the what? Actual cost. So that means at level 0, I am doing F of n. Whatever that function is, I'm doing that is my actual cost. And I'll do F of n at every level based upon its input, and the input is going to be. So at level 1, what is the input size? N over B. So this is going to be F of n over B. How many times? A times F of n over B. That's going to be the work there. You get the idea? And if I go to level 2, it's going to be n over B over B. Okay? And how many of those am I going to do? A squared. Because each of the A branches will have A branches of its own, so you're going to have A squared branch. You get the idea? Okay. All right, so we have A is some kind of positive constant, at least 1. And F is asymptotically positive. We don't have a problem with algorithms. They're always positive. Okay, so there are going to be 3 cases. And I'll spend a little bit of time on these cases, and I'll get a little more, once you learn how to use it, then I'll show you on Wednesday when not to use it, when to be careful with this one. So the common cases have to do with, what we're going to do is, we're going to make a comparison with the actual complexity, which is our F of n, with a quantity, which is n to the log b of a. n to the log b of a. What's n? Problem size. What's b? That's what we're cutting the problem by. And what's a? That's how many branches. Notice that n to the log b of a is also equal to a to the log b of n. Did you know that? We talked about it, but that's okay. We'll come back to it. So the bottom line is, so for example, so n to the log b of a. So if we come over here, let's say for the sake of argument, that b is equal to 2. That means each level is getting a problem cut by 2. And a is equal to 4. So 4 branches, each of them cutting the problem in half. So if b is equal to 2 and a is equal to 4, then we would have log 2 of 4 is what? Is 2, and that therefore we would compare f of n with n squared. Get the idea? That's what we're talking about. If, for example, if the number of branches was equal to 8, and b was still, let's say 2, then we have log base 2 of 8, and that would be n cubed. Okay, so you get the idea. All right, so the first case is the actual work f of n is equal to the big O of the quantity n log b of a minus epsilon. What is epsilon? Epsilon is a very small constant which is greater than 0. So if it's greater than 0, it's positive. Therefore, if it's positive, then I am subtracting a positive, thereby decreasing this polynomial power. Remember, n to the second power is a smaller complexity than n to the third power, is a smaller complexity than n to the fourth power. N to the second power is a smaller complexity than n to the 2.8 power. As the exponent of a polynomial is increasing, the complexity is immediately increasing. So any small increase to a power creates a higher growing function. So therefore, if I have to decrease the exponent of n, whatever the heck it is, by some positive value, I'm simply saying what? That which function, that if I didn't decrease it by this much, then this would be growing, this function would be growing faster than f of n. Okay? So I need to decrease the power of n, decrease it in order to find equality between the actual work. Which means that this exponential n, or this power of n, is actually higher order than f of n. So it's polynomially growing faster. And this one grows polynomially slower. Because you can see that they're equal only after I decrease this one, so it must be polynomially slower. Does that make sense? Okay. So because that's true, and the factor is, of course, n to the epsilon, because if you multiply n to this power by n to the epsilon, the two epsilons will add out, cancel, and you'll get back to this one. So that's the rate, how much faster this one is than that. In this case, what we're going to observe is that t of n is now theta of n to the log b of a. So we're saying that if n to the log b of a is polynomially faster, then the algorithm is t of n to the log b of a. Now, what are the assumptions? Well, the assumptions are pretty clear. The problem is getting reduced by at least a factor of 2 or 3 at each level. So the problem size is decreasing exponentially. That's a given. Why is it a given? Right here. That's the assumption. So the problem is decreasing exponentially. The other assumption is that the number of branches is increasing exponentially. I mean, it could be 1, but generally it's not. It's usually 2, 3, or 4. So if you have 3, you're going to have 3 branches, 9 branches, 27, 81, 243, etc., right? Okay. So in this case, and let's again remind ourselves what f of n actually is. F of n is actually the actual work at level 0. That's exactly what it is. And let's think about what in the heck is this crazy thing. n to the log b of a, which is equal to a to the log b of n. What is the log b of n? Log 2 of n, what is that? It's what? It's the height of the tree. Oh. So, if I flip the n and the a to the log b of n is, log b of n is the height of the tree. And the tree is full because it doesn't have any irregularities. Everything is always the same, cut the same, right? For all peer nodes on the recursion tree. And so if log b of n is the height of the tree, what is a to the log b of n represent?
Number of branches, number of leaves,
Number of leaf nodes. And each of the leaf nodes is doing how much work? Unity. Therefore, if n to the log b of a equals a to the log b of n, that means that how much work is being done on the bottom level. So what we're saying is if the amount of work being done at the bottom level is more than the one at the top level, then the theta complexity is the amount of work being done at the bottom level. Because it means that the amount of work is increasing. Even though the amount of work at each node, at each level, is decreasing exponentially, the total amount of work per level is increasing. It's increasing up to this polynomial from this one, from this work that's bounded by this polynomial. All right. The second case looks kind of weird. Second case is, again, we're going to compare our actual work f of n. We're going to compare it against n to the log b of a, which is, hello, the same thing, right? But we're going to multiply it by log Lg of n to the kth power. Lg means Lg of n to the kth power. That's the notation, right? It just means Lg of n to the power of k. Now, what is k? Well, k could be a constant greater than or equal to 0. If it's a constant equal to 0, then Lg of n to the 0 power is 1. If k is equal to 1, it's going to be Lgn. But if it's 2, it's going to be Lgn squared. So that is something that, so we will compare this quantity, because this quantity is very easy for us to know, because when we look at the algorithm, we can see exactly what level 0 is doing. And we'll see if level 0 can be expressed as n log b of a times any kind of Lg of n to any power. If you don't see any Lg of n, then it's k is equal to 0. If you do see an Lg of n to the second power, then you say k is equal to 2. If you see a power of 1, you say k is equal to 1. If you don't see it, it's equal to 0. I don't see it, it's equal to 0. Okay, so in that case, what we're saying is that f of n and n to the log b of a are growing at similar rates. They're similar. Well, if this represents the amount of work at level 0, and this represents the amount of work at the leaf level, and they're the same, it means that the work is basically staying the same, which is very similar to what we saw where? In merge sort. And merge sort, if I remember correctly, started with n, 2n over 2s, 4n over 4s, 8n over 8s, right? That's a master algorithm approach. Because a, the coefficient a was equal to 2, and b was equal to 2. So we would have to compare the actual work of merge sort, which was n, against n to the log b of a. And that's n to the log 2 of 2, which is n to the 1. You see what I'm saying? So what we had was n to the log b of a for merge sort was n. and f of n was n. And so therefore, f of n, which is n, is equal to the n log b of a times Lg0n. And that tells us that they are growing at similar rates. Therefore, the solution is that T of n is theta n to the log b of a. That means the work being done at the bottom level multiplied by Lg of n to the one higher power than yours. So if your power was 0, now it's 1. And that's what merge sort was. Remember, it was n Lgn. It was n, remember, this is L log base 2 of 2 is 1. So it's n to the first power times Lg of n and Lgn. So that was an example of, we could apply the master algorithm to that one. Does that make sense? I'll give you some more insight into this. It's very, very cool stuff. So here what we're seeing is that the work is essentially staying the same across the levels. So what we're doing is we're multiplying the work at each level by the height of the tree. When k is equal to 0, it's just the height of the tree. When k is more than 0, that means that the Lgn is part of the work being done, in which case we still have to multiply it by the height of the tree. That's why this is growing like this, and I'll show you some examples of that. All right, so let's do, we have another case. So this case is, again, we're always going to compare f of n with n to the log b of a. And again, n to the log b of a, same as a to the log b of n. It's simply the number of leaves with work unity. So it tells us amount of work being done at the leaf level. This tells us amount of work being done at the level 0 level. So what we're going to do is we're going to find out that f of n is equal to some big omega, and then we have to add a little positive epsilon to raise the polynomial complexity of this one for it to be equal, which means that if we have to add it for equality, without it, it's slower. So therefore, the whole algorithm is going to be theta of f of n. Again, the assumptions are that the problem is being decreased exponentially as we go down, and the number of branches is increasing exponentially as we go down. Now, in order for this to work, we also have to satisfy this regularity condition. The regularity condition, so that's one thing you have to check in this case 3. And that is, you want to find out whether there's a constant, for some constant less than 1, you want to find out that A times f of n over b is less than or equal to c times the actual work. So again, let's find out what this regularity condition is saying. So what we're saying here is that we have f of n times c for some constant c less than 1. So this is basically proportional to f of n, right? But a little bit less than f of n. But proportional. So some constant times. So now, what exactly is a to the f of n over b? What is f of n over b? What is f of n over b? Just f of n over b.
Probably divided
It's something. F of n over b is a very specific quantity based upon the master algorithm. Ask your friend over here. He's sleeping. What is that? What is that quantity? F of n. Okay, I'll tell you what it is. You know what f of n is? What is f of n? Actual work level 0. Guess what f of n over b means? Actual work level 1. One of the branches. When I multiply it by a, this is going to be the actual work across all level 1s. So what we're saying is that if you take the actual work at all level 1s, we want it to be less than some amount of. So what do we want to say? We want to know, what do we want to know about the work? What do we basically notice? We're only checking level 1 against level 0 times a constant. What are we checking?
It's
Uh,
decreasing or
it's
increasing?
reducing.
It's reducing or increasing?
So what we're checking is that the work at level 1 is decreasing. If it's decreasing, that's the check. It's the check. If it's decreasing, now it's decreasing, and therefore it's going to be theta of f of n. That means all the work being done in the whole algorithm is proportional just to level 0. And the reason it's decreasing, we only need to find out a little bit here, is because at the decrease, it'll actually be, anybody know what it's going to be? It's actually going to be exponential decrease. And you'll see, I have some different notes that'll make it clear for you guys. So that's the regularity condition. Just make sure that the amount of work at level 1, because once you check level 1 against level 0, then you can do the same thing level 2, level 1, but there's no need for it. So having C be less than 1, you're showing that the work is decreasing. That's all. Okay. So, a little bit of time. Not much. All right. So this first algorithm. Now, the first question I'm going to ask you: does the master algorithm apply?
Yes.
Okay, because we have 4, which is a value. This is going to be our b value. This is our f of n. Okay. So it applies. So we're going to see what's going on here. So we're going to look at it with the value of a is 4, b is 2, n to the log b of a is equal to n squared. N squared. And f of n is equal to n. So, what's going on here? It tells us that the amount of work being done at the bottom level is more than it is here. Therefore, the work is increasing. And therefore, the entire algorithm has a theta of the bottom level, which is n squared. Okay, so let's take a look at example 2. So here we have t of n is equal to 4t of n over 2. Notice it's the same thing here. The only difference here was we have n squared for our actual complexity. So again, our n to the log b of a is still n squared, same as before here. And our f of n is also n squared. So now we want to find out can we set up an equality between f of n and theta of n squared lg to the k of n. And we can only if k is equal to 0. So k is equal to 0. So because we can set up this equality, that means the work being done is proportional on every single level. They're about the same. So therefore our complexity is going to be n squared lgn. So this is just going to be f of n times lg k plus 1 when k was 0. So it's k plus 1 is 1 of n. All right? All right, we'll stop right here. See you guys.